So there are actually only 4 fundamental forces of nature, and all of the forces that we have talked about, all those everyday forces, actually just come from these 4 forces, which is the electromagnetic force, force of gravity, the strong force, and the weak force. So in class we're going to talk a little bit about the strong force and the weak force, but in this video we're just going to deal with briefly the electromagnetic force, and then we'll really focus on the force of gravity. So the electromagnetic force, I'm just going to mention briefly because we have actually a whole unit coming up on the electromagnetic force. But basically there's sort of 2 components to it. There's an electric part and a magnetic part, and those work together to make the electromagnetic force. Electric forces can attract or repel any object with charge. So you're familiar with this. Opposite charges attract, right? So there'll be a force of attraction there. That's an electric force. Like charges repel. It's a repulsive force there. The electromagnetic force acts at an infinite distance. So it can act very, very far away. That's quite unlike the strong force and the weak force. But it doesn't act at the same strength as it goes to further distances. So the further away you are, the weaker the electromagnetic force gets. So if you have 2 charges maybe that are attracted to each other, if you bring them very far apart, they'll still feel attracted to each other, but it'll be a weaker force. So every one of these fundamental forces has a force carrier. That's a tiny particle. So this is in the particle physics model. It's a tiny particle that carries the force from one object to the other object. So how does the force get from this positive charge to that negative charge? How does it communicate? That's with a tiny particle. And the photon is the force carrier for the electromagnetic force. That should come as no surprise, because the photon is actually that's a particle of light, right? And electromagnetic waves, the light is an electromagnetic wave. So when we talk about light, we can talk about it through a particle model, talking about photons. We can also talk about it through a wave model, talking about electromagnetic waves. Of course, in real life, it's actually both. Just as a little historical aside, so how this electromagnetic force came to be, for a long time physicists used to believe the electric force and the magnetic force were 2 completely separate forces that acted on just different objects in different ways. But in the mid-1800s, a really famous physicist called Maxwell created a set of equations that are called Maxwell's equations that actually unify the electric force and the magnetic force, and showed us that really these are just 2 faces of the same force, which is the electromagnetic force. So this was a unification of 2 forces into one force, the electromagnetic force. And that's something that physicists are still trying to do, trying to unify more of the fundamental forces into a smaller number of forces. Maybe just one force is sort of the ultimate goal of the grand unification theory of physics. All right, the gravitational force. We'll spend a little more time here. So first we're going to start with a Newtonian picture of gravity. So that's the picture of gravity we'll use mostly in this course. Gravity, first, is very similar to the electromagnetic force, but it has a few interesting differences. One is that it's only attractive. We've never observed repulsive gravity, so it's always an attractive force. And instead of being between objects with charge, it's between objects with mass. But like the electromagnetic force, it also acts at an infinite distance. So you see, this is going to be very different when we get to the strong and the weak force. The strong and weak forces act at really tiny distances. The force carrier of the gravitational force, we've actually never observed, but it's proposed to be the graviton. If we ever see it, that's what we're going to name it. We haven't seen it yet. That's the proposed force carrier. Okay, so in class we've talked about a simple equation for the force of gravity, which is Fg is m times g. But this only works on the surface of the Earth, or on the surface of any planet that you know g for. So this really only works on the surface of the Earth. So it's a really simplified picture of gravity. But gravity is acting between any force with mass, right? There's gravity between the moon and the Earth, or between the sun and the Earth. We could be talking about distances that are much bigger than just us on the surface of the Earth to the center of the Earth. So if we want to talk about the force of gravity in general between any 2 objects with mass, then we need a more general equation, and this equation is that general equation. So the force of gravity is this constant, big G. Big G is very different from little g, which is 9.8 on the surface of the Earth. Big G is 6.67 times 10 to the negative 11. So that's the gravitational constant there. multiplied by mass 1 times mass 2. So the gravitational forces between any two objects with mass, so mass 1 and mass 2 is a good name, divided by d squared. And d is the distances between the centers of the object. So if I want to know the gravitational force of attraction between this tape and this eraser, I need to measure the distance between the center of the tape and the center of the eraser, or the center of mass of the tape and center of mass of the eraser. All right, that is my equation. Let's try using it. So we have student A. Student A claims to be attracted to student B. So here's student A, draw my little picture. And she says she's attracted to student B over here. She's wondering if maybe her force of attraction that she feels towards student B is caused by gravity. So we're going to check for them. So the mass of student A is 130 pounds. Just write down my given here. The mass of student B is 150 pounds. And the distance between their centers, so this distance right here, is 2.5 meters. So D is 2.5 meters. And what we're required to find is the force of gravity that student A feels from student B, and conversely that student B feels from student A. So first off, I'm going to need to make some unit conversions here. Pounds, I can't use that, that's not an SI unit. So here's my conversion for kilograms to pounds. So I'm going to do 0.45 kilograms is equal to 1 pound. That cancels out my pounds, right? So this is gone. And I'll just calculate that here. So 130 times 0.45 is 58.5. So mass of student A is 58.5 kilograms. Same idea with student B, so 0.45 kilograms divided by 1 pound. My pounds cancel out here. There we go. And I get 150 times 0.45 is 67.5. And the distance is already in SI units, so it's good. Okay, so my equation for the force of gravity is big G, that constant, times mass of student A times mass of student B. So these are the two objects that are gravitationally attracting each other, divided by the distance between them squared. Let's just plug in all our numbers. So big G is 6.67 times 10 to the negative 11. It's a constant. The mass of student A in SI units in kilograms is 58.5. Mass of student B is 67.5. And the distance between them is 2.5 meters, and that's squared. All right, toss this all into your calculator. 6.67 times 10 to the negative 11 times 58.5 times 67.5, all divided by 2.5 squared. All right, I get 4.2, and it looks like I've got two sig figs here because of the distance there. So 4.2 times 10 to the negative 8 newtons. So that means my force of gravity, if I were to write this out not with scientific notation, it would be 0.000000042 newtons. That's a really tiny force of gravity. So there is actually a tiny gravitational attraction from student A to student B. So she feels a little bit of a force of gravity pulling her towards student B. And student B will feel the same force of gravity pulling towards student A. But probably it's not too likely that this is the force of attraction that student A feels. It's a pretty small force. It's pretty negligible. You won't really notice a force that small in your everyday life. Let's look at an object that causes a force of gravity on you that you will notice in your everyday life. That's a much more massive object. So the reason why the force of gravity here is so small is because the masses of student A and student B are so small that they can't exert a very big force of gravity. Because the gravitational constant is so big, you have to have a lot of mass in order to make a meaningful force here. An object that has a lot of mass, which is near us, is of course the Earth, right? So we are currently on the surface of the Earth. I think you're watching the video from the surface of the Earth. Let's figure out what the force of gravity is on a person of mass m. We'll just use the variable m to keep it nice and general, who's sitting where you are on the surface of the Earth. So the radius of the Earth is 6,371 kilometers, and the mass of the Earth is this. So let's just draw a little picture of, here's the Earth. and here's you. So you're just standing here on the surface of the Earth watching this video. The distance between your center and the center of the Earth, that distance d, is basically just the radius of the Earth, isn't it? I mean, there's the tiny distance from your feet to your center, but that's pretty small compared to the 6,000 kilometers from the surface of the Earth to the center. So basically the distance between your center and the Earth's center is the radius of the Earth. Let's write down our given then. So we just figured that out, that the distance between the center of you and the center of the Earth is the radius of the Earth, which is 6,371 kilometers. I'm going to need to switch that to meters, right? So there's 1,000 meters in 1 kilometer. So that kills my kilometers here. So I could write that all, it'd be 6. I'm going to need to add 3 more zeros there to put it in meters. I know the mass of the Earth. That's the 5.972 times 10 to the 24 kilograms. So that's a massive object, right? That's big enough to really exert a force of gravity. What I'm trying to find, so my required, is the force of gravity on you. And we're just going to call your mass m, because then that lets us be a little more flexible. So the force of gravity in general is big G times the mass of the Earth times the mass of you, we're just calling that m for now, divided by the distance between the center of the Earth and the center of you squared. Let's plug in our numbers. So that'll be 6.67 times 10 to the negative 11, that's big G. Mass of the Earth, 5.972 times 10 to the 24. Mass of you is just m. That's not meters, that's like mass of you right there. Divided by distance squared, so that's the 7 meters, and that's all squared. I don't have to write the units in here, I guess, because I'm just calculating right now. So 6.67 times 10 to the negative 11 times 5.972 times 10 to the 24. What I'm going to do is just leave the m on the side, just calculating this part right here. I'll get a number for all of that. And then we'll have that number times m. So I've done the top so far, just need to do the bottom. So divide by the 6,371 squared. And I get a very familiar number here. So the number that I get is 9.812 and then times m, right? So that's the force of gravity. This part right here is actually the acceleration due to gravity, right? That's little g, 9.8, around 9.8. It varies a little bit depending on where you are on the surface of the Earth. But what you can see, so we've simplified this general gravitational equation to the one that we use all the time. The force of gravity is mg. We can actually calculate g if we plug in the gravitational constant, the mass of the Earth, and the radius of the Earth on the bottom. That gives us a little equation for the force of gravity right at the surface of the Earth, right here. So m is your mass, that's the mass that's feeling the gravity, and g actually involves the mass of the Earth, the radius of the Earth, and our gravitational constant. That's actually our little acceleration due to gravity right there. Let's do one more example using this Newtonian picture of gravity and using our general equation for gravity that works beyond just the surface of the Earth. Our force of gravity is big G m1 m2 over d squared. We'll do it in the situation of the sun and the Earth are pulling on each other. So I'll do a little picture here. We've got the sun, who always wears sunglasses, you know, there he is. That's the sun. Then we have the Earth over here, quite a lot smaller, it's not to scale. The distance between them is d, and it's the distance between their centers. Oh, sorry, that was supposed to be a straight line. That's the distance between them there. Let's write down what we know about the sun and the Earth here. So our given information, I know the mass of the sun is the 1.99 times 10 to the 30 kilograms. I know the mass of the Earth is 5.97 times 10 to the 24 kilograms. And I know that distance between the two, d, that I labeled here, it's this insanely giant number, but we should probably convert this to meters, right? It's in kilometers right now. And that's not going to work. We need meters. So 1,000 meters is 1 kilometer. So that cancels my kilometers out. And let's just write this in scientific notation to make our lives easier. So let's see. If I slide my decimal place from here, there's 1, 1, 2, 3. Here's another 1, 2, 3 spots I'll have to slide. 1, 2, 3 spots, and then another 2 spots. So that's 11 altogether. 11 spots that I had to slide my decimal place. In other words, that's 10 to the 11, 11 powers of 10. So I'll have 10 to the power of 11 meters. That's the distance between the center of the Earth and the center of the Sun. Okay, I want to actually calculate the force that the Sun exerts on the Earth. So that I'll call Fg. And it's the force that the Sun is exerting on the Earth, so maybe I'll call it Fgs because it's like the force from the Sun. I'll label it on here. The Earth feels this force, Fgs. That's equal to, will be mass, the gravitational constant, mass of the Earth, mass of the Sun, divided by the distance between them squared. All right, let's plug in all our numbers. So big G is 6.67 times 10 to the negative 11 times the mass of the Earth, 5.97 times 10 to the 24 times the mass of the Sun, 1.99 times 10 to the 30, divided by 1.496 times 10 to the 11, that's squared on the bottom. I get 3.54 times 10 to the 22 newtons. So the Sun exerts a very big force of gravity on the Earth. All right, so looking back at our picture, well then what is the force that the Earth exerts back on the Sun? Right, the Sun is pulling on the Earth. Does the Earth pull on the Sun at all? Well, actually, Newton's third law would say that for every action there's an equal and opposite reaction. So that means that if the Sun pulls on the Earth with this force, then the Earth must be pulling back on the Sun with the exact same force. So the force the Sun exerts on the Earth, the force the Earth exerts on the Sun, so this is the force of gravity that the Earth is exerting on the Sun, so the Sun feels from the Earth. I'll just draw it on our picture here. So this force right here, Fg from the Earth, that force is exactly the same size as the force of gravity that the Sun exerted on the Earth. The only difference between them is that the force of gravity that the Sun exerts on the Earth is towards the Sun, and the force of gravity that the Earth exerts on the Sun is towards the Earth. So Newton's third law says that these action-reaction pairs are in opposite directions, right? So towards the Sun or towards the Earth, there are two opposite directions. You can also figure this out if you don't remember Newton's third law. You can just use the equation, right? We would use the exact same equation to calculate this again, because one of the masses is the Earth, the other mass is the Sun. The distance between them doesn't change, the gravitational constant doesn't change. You're going to get the same number. What feels weird here is that the Earth gets influenced by the Sun a lot. It really moves a lot because of that force of gravity, and the Sun doesn't move so much at all, right? The Sun is just chilling with his sunglasses on, and the Earth is like, here's the Sun, there he is, and there's the Earth is like orbiting around the Sun, like he's really influenced by the gravity of the Sun, and the Sun doesn't really seem to be influenced by us at all. So why is that? Well, that comes down to Newton's second law. So Newton's second law is that the net force is equal to the mass times the acceleration. Let's just pretend, to make our lives easier for a second, let's pretend the Earth and the Sun are the only two things in our solar system. So we'll just pretend that the net force on the Earth is just the force of gravity from the Sun, and the net force on the Sun is just the force of gravity from the Earth. So we're going to pretend there's nobody else, no other planets out there, no other moons or anything like that. In that case, then the net force that the Earth feels is going to be this force of gravity from the Sun, which is pretty big. The mass of the Earth here is not as big as the mass of the Sun. So that means the acceleration of the Earth will be a decent size. Whereas if I use the net force on the Sun here, well then the net force on the Sun would be just the force from the Earth in our hypothetical solar system. But the mass of the Sun is huge. So when I'm calculating the acceleration of the Sun, it'll have to be really, really small. And so that's why the Earth ends up accelerating a lot. Its acceleration is towards the sun, and that's the acceleration of the Earth. That's what causes it to go in a circle. You're going to learn more about centripetal acceleration and circles and stuff in grade 12. And the sun actually does feel a little tiny acceleration towards the Earth, but it's so small, the sun doesn't really move a lot from it. It doesn't really influence the sun very much. Let's actually just quickly calculate those. So if the net force is mass times acceleration, could divide by mass on both sides and get the acceleration, right? So acceleration is net force over mass. For the Earth, I'll do that one first. So acceleration will be the net force on the Earth feels here, divided by the mass of the Earth. So the net force that the Earth felt is this 3.54 times 10 to the 22. We're going to divide by the mass of the Earth. So that's 5.97 times 10 to the 24. The acceleration of the Earth is going to be 5.93 times 10 to the negative 3 meters per second squared. If I do this for the sun, just move this up a bit so you can see, the acceleration of the sun is going to be the net force on the sun divided by the mass of the sun. It's going to be a much bigger number on the bottom here, which is going to make a much smaller acceleration. So 3.54 times 10 to the 22 divided by 1.99 times 10 to the 30 gives me 1.78 times 10 to the negative 8 meters per second squared. So it's a super tiny acceleration, which is why the Earth moves a lot and the sun doesn't really move much at all. Right, so that's it for our sort of Newtonian picture of gravity. That works really well in most instances in life, but I thought I'd give you just a brief introduction to the modern physics perspective of gravity. So early in the 1900s, Einstein had what he called the happiest thought of his life. What he imagined is, let's say you're inside an elevator. So this is you in an elevator. Maybe it's an elevator on Earth, maybe it's an elevator in space though. You don't know. And all you see around you is just the walls of the elevator, the floor, the ceiling. That's all you've got. And you feel what might be a force kind of pushing you down to the bottom of the elevator. So that force could be gravity. Maybe you're sitting on a planet or sitting on Earth or somewhere close to a planet, and so you feel a force of gravity pulling you down. So maybe that force there's a force of gravity there. Or maybe you're super far away in deep space. There's no force at all. There's no force of gravity at all. It's just an acceleration that you're accelerating upward, and so you feel like you're being pushed down into the floor because of your inertia. Maybe that's all it is. So what Einstein's theory of general relativity was that these two concepts, so gravity and acceleration, maybe they don't just feel the same. We can't really tell if we're in this elevator whether I'm feeling gravity or I'm feeling an acceleration. Maybe they actually are the same thing. Maybe it's not just that they feel that way, but maybe there is no difference at all. So his idea was that maybe the force of gravity isn't actually a true force. Maybe it's just that massive objects sort of bend the fabric of space, and then other massive objects around them will follow curved lines in space and behave in the ways that we've been predicting using equations like, this is the Newtonian equation, Fg is g m1 m2 over d squared. So this equation predicts how objects behave, but maybe they're behaving this way not because of a force, but because of acceleration in space that's actually been curved. That seems almost impossible to prove, right? Like how do you show this with an experiment? But actually there's been an experiment done. So this is pretty creative and really cool. If you think about us here on Earth, so this is us, we're the observer, this is the sun. Well, of course, as the Earth is moving around the sun, there'll be moments when stars are directly behind the sun relative to us, right? So if a star is directly behind the sun, we shouldn't be able to see that star at all. That star is really far away, so it looks really tiny to us. The sun is quite a lot closer, so it looks really big to us. So the sun should completely block out the star. What we see happening is that if we really closely follow the position of a star, as the star appears to move behind the sun, this is just because of the motion of the Earth, right? As the star appears to move behind the sun, it looks like the light from the star is sort of actually over here. So it should be behind the sun. It looks like the star is over here. The reason for the star appearing to sort of jump or move in the sky is because the light from the star has curved around the sun and gotten to our eye. Well, that would make a ton of sense if photons, which are little particles of light, had mass, because particles with mass would be attracted by a force of gravity to the sun. That would kind of change their trajectory. Imagine that photon's a little spaceship, right? If it went close to a massive object like the sun, it's going to bend closer into the sun. It'll not quite follow an orbit if it's going really fast, but it'll at least bend in a little bit like that. What's weird about this is that that is not a spaceship, right? That is a particle of light, that's a photon. And photons have no mass. So if we only use the Newtonian picture of gravity, the force of gravity is g m1 m2 over d squared. Sure, the mass of the sun here, that would be m1, is really big, but the mass of the photon is exactly 0. And so the force of gravity that that photon feels should be 0. That would mean that photon should not bend at all. It should just go in a straight line. We shouldn't be able to see the star. The star should be perfectly behind the sun and its light should travel in straight lines, and so we can't see it at all. Except that we can. And so the fact that we can see it, and it appears to have moved to this position, must mean that somehow that photon is being pulled by gravity, or maybe that gravity isn't really what's going on here. Maybe the sun is actually bending the fabric of space, and then that photon is just following a line in space which happens to be curved around the sun. So if this was sort of the sun here, and this is the star, which is directly behind the sun, that light shouldn't reach us at all because there's the sun in the way, but instead it curves around the sun and reaches our eyes, and we think we see the star over here. It sort of appears to move over here in space. Pretty crazy, but that's a natural experimental verification of Einstein's theory of general relativity. So think about it, is there any mass you know of that could really warp space so much, just bend space so much that the light doesn't just sort of curve as it goes nearby that massive object and follow those curved lines, but actually falls into that hole and can't get out again? So you can no longer see, that photon is just gone forever, you no longer see it. There is, so these masses, you see them, there's one in the center of our galaxies. That is a black hole. So a black hole has a thing called the event horizon, where inside that sort of region, even light that's traveling super fast trying to get out cannot get out. It falls into that black hole, and so it's black inside there because light can't escape from that hole. So we can't see anything there. Nothing can escape from that hole. Just outside the event horizon, you'll usually see lots and lots and lots of light. That's because things are falling into the black hole, they're crashing into each other. That at least is in an active black hole. If there's no matter moving into the black hole, then it'll be pretty boring to look at. It'll just be black. You can't see much at all. All right, so that's a little very, very brief or very rough introduction to Einstein's theory of general relativity. It's a lot richer than that. That was a pretty brief overview. It's a really beautiful theory, and it's a lot more complete than Newton's theory. But the reality is, for most of our life, we don't need to go that far. So for most of your life, you can use like Fg is g m1 m2 over d squared. That's if you're dealing with anything in space or gravitational attractions between any object other than your object and the Earth, and you're sitting on the center of the Earth. But actually, most of the time, all of this, all of this stuff here, if you're talking about some object, mass 2 is just some object on the surface of the Earth, then mass 1 becomes the Earth, and d becomes the radius of the Earth, and all of this just simplifies to that number 9.8. And then you can just use an even simpler equation that the force of gravity is just the mass, that's like your m2 here, times the acceleration due to gravity. That works just fine to make most predictions about our world.